Welcome to Introduction to Quest, an online resource to get started on Northwestern's high-performance compute cluster. To participate in the interactive portions of this online workshop, you will need an account on Quest. To learn more, please visit the links on your screen. We're going to learn about Quest. We're going to find out about high-performance computing. Why do you want to use Quest? And as part of that story, I'm going to tell you about research computing. Alper and I are both in research computing. You're going to learn more about Quest from a systems point of view, what it is, how to get access to Quest through research allocations, some information on parallel computing, what makes Quest special, how can you use Quest how can you leverage the specialness of Quest to make your research move faster using parallel computing. File sharing, what's the best practice to get files on and off of Quest. And we're going to be logging in and doing some job submissions so that you will have that under your belt. You'll have seen how it's done and have some tools to monitor your jobs when they run. I mentioned research computing. So this is a group of the consultants. I'm Jana Nugent, I'm right there. Let me tell you a little bit about my background. So I used to be at the University of Chicago. I was in academic computing there. Some of the capstone projects I worked on is I ran molecular modeling laboratory, and then I went back and got my master's degree in computer science from the University of Chicago. And in 2016, I started working here at Northwestern. So my background is computer science. I have a specialty in bioinformatics for computational research. Also work in data science, support cloud computing and data workflow. So that's my background. And then here's Alper. Alper is our TA today. Alper is a senior computational specialist. We work together to support people across pretty much everywhere at Northwestern today. And other members of our team help provide support around data science, cloud computing, visualization, data management. If any of these things sound like topics that you'd like to explore further, please don't hesitate to reach out to quest-help@northwestern.edu. And I just want us to hear Alper's voice for a minute. Good morning, Alper.
Good morning, Jana.
All right, so we're going to dive in right away with logging into Quest. If you already have an account and you already have a way that you log into Quest, go ahead and do that. So you don't have to log in the way I'm going to describe right now. If you do not have that method already in place, then we're going to be logging you in through the web browser, all right? And that only works if you're connected to Northwestern's VPN. So from your browser, you need to go to http://quest.northwestern.edu:3000. The only catch about this is you do not do HTTPS, just make sure it's HTTP. And again, you need to be on the VPN for this to work. So if you get this part, fastx with that little fancy star, that means that you were able to connect. So this is already sitting at Quest. This is Quest's front door for you today, and this is how you need to get in. If you are trying to do this and you do not see this, the two errors that I expect have happened to you is either this HTTP was HTTPS, or you're not on the VPN. So I'm just going to walk you through how to log in from here. So this is, you put in your usernames and your password. So your username is your net ID, and it's the Northwestern Federated net ID. One of the nice things is that Northwestern propagates your password everywhere. So if you ever, how every year you're supposed to change your password on Quest will automatically get changed at the same time. So in fact, on Quest, we don't store your password. We always query the central server and check out what it is at any given moment. So log in with your net ID and your password, and you'll see a screen that says My Sessions. Click on the Launch Session button. So that's that blue button on the left. Click there. And now you're going to see a number of icons. So I'm not sure that the icons look the same for everybody. There might be a different collection, but today what we're going to be picking is GNOME Terminal. So go ahead and select the one that's GNOME Terminal, G-N-O-M-E, and then click Launch. All right, so once you've hit Launch, it's going to look like this. So now you are logged into Quest. What you see here is a prompt. The net ID is at the front part of that, so that's my net ID today. And then QUser21 is a login node. And we're going to talk about that shortly. All right, so I'm going to keep moving from here. When I think about where things are going to be challenging, this is kind of a potential hurdle. It's not surprising if this part was not smooth. When you log in, if you log in the method that we just did, you don't see the message of the day. We're still working on getting that to display through the web browser. However, the other methods of logging in typically will show you message of the day. So on a Unix system machine, like the login nodes are, when you log in, there's an opportunity for the people who support the system to tell you about what's going on with it. So we do that. There's a combination of items that are always there, and then some updates might be at the bottom. But I thought, instead of telling you what Quest is, I thought today what we could do is show you what Quest is. And so let's start by listening to what Quest is going to tell us about itself. So of course, Quest, right? So I remember teaching this once, and I was about halfway through and someone said, so what is Quest again? And I realized I never really explicitly said Quest is the name of our high performance compute cluster at Northwestern. It's not a brand name, it's a name that's referencing the hero's journey of scientific discovery. Other institutions have other fancy names, like I enjoy that Stanford has Sherlock and Harvard has Orchestra, Texas has Stampede, and Northwestern has Quest. So the next thing we have is welcome to Quest's high performance compute cluster. So let's talk about high performance compute cluster. What is that exactly? So we're going to break this down starting with the compute cluster part of it first. So a cluster is a group of a thing, right? And in this case, it's a group of computers. We have 750 computers that work together to solve complex problems. That's what Quest is. So one of the terms that's immediately kind of different is that those computers, we don't call them computers, we call them nodes. So the term node here kind of comes out of graph theory, if anybody had to take that kind of class. These are computers that are very similar in a way to what you've got on your laptop, except they don't have a monitor and they don't have a keyboard. They're designed to be modularly placed in these racks so that they can be held in a very dense formation, so that they can have networking connections that are both high speed. So we have this thing called InfiniBand that lets them communicate at high enough speed that they can act as if they're one computer instead of a bunch of different separate computers. And then Quest, so this picture, I like this picture. This is actually baby Quest. So this was Quest quite a few years ago. Quest today is maybe 3 or 4 times the size of what we're looking at right now. But one of the other things I like about this picture is you can see in the far right that there's this window. So there are people there on site 24/7 taking care of Quest and making sure that everything runs. It's under security. There are guards there. It's on a high-speed network, both to the Chicago campus and because it's located in Evanston, and on a regional network. So that's what Quest looks like. If you were standing here and we were talking, you'd have to shout because there's a lot of air conditioning to cool down from all the fans and all the computers that keep the space hot. All right, so compute cluster, there's the cluster. From here on out, we're calling those computers nodes. So a node is a single computer unit. Now I said it was somewhat like your desktop, but now we need to talk about high performance. It's not the same class as what we typically experience on our desktop computers. You can see that, for example, so processor speed, how fast it runs, Quest can run faster. How many cores, we'll talk about that in a minute, but that's how many units can do independent processes at a time. So typically a desktop computer has 2 to 4, and Quest will have 24 to 40 on each of those nodes. And then memory, so RAM, a typical desktop computer has 8 gigabytes of RAM. And on Quest, our nodes have between 96 and 192 for most of them. We even have a couple of 1 terabyte RAM nodes. So the other part of the high performance picture, of course, is that for most of us, we have 1 desktop computer, but we have 750 of these all working together. That's what makes up Quest. And because we have 750 of these, Quest has 25,000 cores. So that's 25,000 units that can perform independent processing at any given time or can work together. So let's talk about the core part a little bit more. So as we said, each of these nodes has between 24 to 40 cores. So cores get named a couple of different things. I've heard them called processors and CPUs. I've even heard them called tasks. They are what threads run on. So the language around core can seem somewhat ambiguous, and that's just sort of how that historically is described. So it is a little bit tricky to keep that one separate from, for example, what the node is. A node is always called a node. A core might be called a processor or a CPU. Let's break that down a little bit. So this is taking a close-up look at one of those nodes and examining what its cores might be doing. So for example, each node, so this is a single node here, is running jobs from a number of different researchers. I have it set up now that we've got Python on one, Fortran and R. A researcher can run on a single core or can run on multiple cores. For example, we've got 2 cores being shared for this MATLAB job and 3 cores being shared for a GATK job. So you can see how nodes can have a combination of researchers and jobs running at the same time. And I've started to use the term job, and I want to just be really explicit about what that is. A job consists of a prepackaged sequence of commands run on a node for a user. So we just looked at what happens when a bunch of researchers run on a node at one time. But you can also take an entire node as a single researcher and use all of the cores for your own threads. So you can fill it all up with a single job that's sharing all the resources on the nodes and actively using all of those cores. You can also use it by having many jobs running on each of the individual cores. So in this case, these jobs are not communicating with one another. They're just running at the same time on this same node. So on Quest, each researcher can run thousands of jobs at once. And you can actually have up to 5,000 jobs waiting to run at any given time. Well, it's a combination of running and waiting to run. When you break up your computation that way for parallel computing, it's called high throughput computing. High throughput computing historically also had the name embarrassingly parallel computing. The sense was that it was embarrassing if you couldn't figure out a way to make it run in parallel because it didn't need to communicate. The jobs don't need to communicate with each other. You can break up your work into tiny little independent pieces and run them all simultaneously. So an example of this is actually in the realm of genomics. When you're aligning a genome, the different segments of the genome, they don't actually care where the other pieces get aligned to, so they can all work independently. And in a case like that, you can run many jobs at the same time with all the little different pieces writing into files, which you either combine at the end or even writing at the same file if you want. Here's another model for how you can do parallel computing on Quest. In this example, we have 4 nodes that are all running the same person's job that's being coordinated. So those arrows are indicating there's communication between the nodes to just sort of keep track of the work that the different nodes are doing and making sure the work is being distributed out evenly to all of the cores. In a case like this, you would distribute out work, probably bring back some results, perhaps distribute more work out based on those results and kind of unify that at the end and write a final conclusion. So this kind of parallel computing typically requires software like OpenMP or MPI. In these cases, it is complex to write software to be able to do this. And because it's complex, it's unlikely that most open source software is written to run on multiple nodes. Most open source software can run on multiple threads where you can occupy them on the same node. But once you start running a job that takes more than one node, now it's unusual to find open source software that can do that. So check the documentation of the software that you're running. Make sure it explicitly says it can run on multiple nodes before you reserve multiple nodes for a job like that. The next thing that we see in the message of the day is that Quest has 4 node architectures, which you can specify in your script. Here's our cluster. It's divided out into pieces. So every year, we typically will buy some new nodes and retire some old nodes on Quest. But that means that we usually have 3 or 4 different generations of nodes on Quest at any given time, because we always buy the newest and best, but of course that, a year later, there's something newer and better. So in some cases, it's important to pay attention to which of these architectures your job runs on. So it says Q5, that's Quest 5, Quest 6, Quest 8, Quest 9. There's more information about this in our documentation. So for today's purposes, just be aware that Quest isn't just one type of node reproduced everywhere. There are multiple generations of nodes available for you to run your jobs on. So users cannot request more than 4 cores and or 4 gigabytes of memory in total for all commands and code they're running on a login node. All right, so what is a login node then? Going back to our cluster here, the compute nodes. So most of the nodes are actually dedicated for computation, but 4 of the nodes are dedicated as login nodes. They go by these names: QUser 21, 22, 23, and 24. You can see that I was logged into QUser 21 when I did my login session earlier. Your login session, these are distributed depending on the load at any given time. So today you might land on QUser 22, and then next week you might be on QUser 24. And that's fine because those 4 machines are identical and they look at exactly the same file systems. So you really won't notice a difference between them. All right, so now we're going to do some interactive parts on Quest. So I want you to go to your login session. There it is, login session. And we're going to start running through the commands. If you have it up from the GitHub repo, we're going to start with part 1. So the first thing I like to start with is this command called who am I? So it goes like this, who am I? So I can see that that's my net ID. So I was mentioning that the login nodes are shared, right? So we have a lot of users at any given moment who are logged onto Quest. So let's see who's on our particular node. So I'm going to use the W command. And that's going to show me everyone who's logged in right now on this particular login node. The point of the W is just showing you that there are a lot of people doing a lot of things on Quest on these login nodes at any given time. On the message of the day, when it said, if your job uses more than 4 cores, it will be killed, or if it lasts too long, it'll be killed. That's why, because it's a shared resource. What people do on the login nodes is we write some code. We can move files around. You can, if you have, say, a pipeline, you can test it using a toy data set. So just a really small data set to make sure there aren't any obvious bugs. So you can get ready to run your jobs on the compute nodes, but a login node is not where you're going to do most of your heavy lifting with your computation. All right, so the next command we're going to do is pwd, which stands for print working directory. So the commands we're running here are Unix command line commands. If you're unfamiliar with Unix command line, I strongly suggest that you visit some of the resources we have available to learn some more about it. It's not obvious. It's been around for a long time. So the Unix command line, there are a lot of resources available. If you Google, you can start learning about how to use it. And it is very powerful. So it's the primary way to access Quest for launching jobs. I am in my home directory. Everybody on Quest gets a home directory like this, /home/netid. Your home directory is 80 gigabytes in size. That's how much space you can fill up. So let's take a look at what's happening in our home directories. The command homedu brings back a detailed disk usage report. Home directories are backed up. Home directories are the only part of Quest that's backed up. So a home directory is a place where if you did delete a file, you can open a ticket and we can often recover that for you. But anywhere else, if a file is catastrophic, if you lose it, you'll need to make sure it's backed up to another location. So homedu is important because if your home directory gets completely filled up, then you will not be able to log into Quest. That's because when the act of logging into a Unix machine, you have to write a tiny file as part of that process. And if there's no room in your home directory, that tiny file can't get written. And then we'll have to delete some files for you. I want to also take a look at what groups I belong into. And on Quest, a group is an allocation. So type the word groups. Each of these is, each one that starts with a B or a P or a W is an allocation. And we're going to be talking about allocations in more detail later. For today, when you launch jobs, you're going to need to know the name of your allocation that you're launching to. So typically the first thing in the list is your netid. The allocation you were added to most recently is going to be the farthest over on the right. That might be the one that you're doing today, but I would suggest at this moment, go ahead and write down or take a note somewhere of what your allocations are, specifically the ones towards the right-hand side, because we're going to need those for launching a job later in this workshop. So I'm going to go ahead and look up one of these projects. We have a tool to do that. So let's do check project. So I can use the check project command for any project, any group that I belong to. So I've used 3 words interchangeably here, if you guys have noticed. So I want to just call that out. Groups, allocations, and projects, right? So the group and the allocation are really the same thing. A project is another way that we talk about allocations. So check project is going to look at this allocation and give me more detailed information about it. Allocations on Quest have expiration dates. We'll talk about that more later. This is how you can find out what your expiration date is. So the next command we're going to run is setting up for being able to launch jobs. We're going to make a directory. So in the Unix command line, that's make dir. And what we're going to call this today is quest _ intro. Okay. So I'm going to now move into that directory, which I use the cd command, which is change directory, quest _ intro. All right, so to feel like I really am where I think I am, I'm going to run pwd again, print working directory. And now I have the full path name and I can see I'm in my home directory and I'm in this quest intro directory. Now I'm going to copy a file in. This is important to get this correct with the syntax. Copy is done through the cp command. The cp command starts with the thing I want to copy into the thing, the new thing, right? So the thing I want to copy today is projects intro job script.sh. So that's what I want to copy. And I'm copying it into the directory that I'm in with that same name. And in Unix, the way I can do that is I can just have a dot, because the directory I'm in is always a single dot. And now, just to make sure that that's really there, I'm going to type ls, which is list. So show me what's in there. And there it is. So that's the end of this part one of the interactive. So we're still working through the message of the day. A couple of things to know about Quest. Quest is not HIPAA compliant, and it is not approved for contractually or legally restricted data. So there are a number of standards out there today for getting different data sets, whether it's related to patient data or database data that comes from the EU that has particular privacy guidelines around it. If you have any questions about it, reach out to us and ask. This is definitely a field where things are shifting frequently, so we can help connect you with the right resource if Quest is not it. This is a link to our webpage. So we have information. So sometimes, like if you're writing a grant, you might need to know specifics of the technical specifications of Quest, or you might be curious. People are asked to cite Quest if it's contributing to your research for papers. We have lists of our software, how to apply for allocations or join allocations or renew them. So all the Quest related information you can find. This is kind of the gateway. This will get you started with that. Here we say that Quest enforces memory limits on jobs. So what that means is that if your job is running on a compute node and it asks, so you've reserved a certain amount of memory and your job wants to use more than what you've reserved, your job will not be able to do that. In some cases, your job will be able to adjust and say, oh, I wanted a lot of memory, I only get this medium amount because that's all I reserved. That's fine, I'll make do. And sometimes your job will just be killed at that point. The good news is if your job is killed at that point, you'll get a really nice all caps out of memory error message. It's very clear. But when you run your job, you will be reserving a particular amount of memory. Be aware if you try to use more than you reserve, that your job will probably be killed at that point. We have a storage and data policy. I would encourage you to take a look. The takeaway that I really would encourage you to have today is to just be aware that data cannot live on Quest forever. When you apply for an allocation or when you purchase storage, there is an endpoint to that period. So that's a year for the general access allocations, and it's 5 years for purchase storage. And at the end of that time, you're going to need to get that data off of Quest. So it's not a bad idea to think in advance, well, where can I put this a year from now? Do I need to keep it? Do I need to, archive it? Does it need to stay active at some other location? Just be aware, because it will be deleted off of Quest. And then I just want to circle back around to reaching out to Quest-help if you want to purchase nodes or storage, or if you have any questions around how to use Quest or any assistance with using Quest. Please reach out to us. That goes to the whole team, and we can make sure to connect you with the right resource for your question. All right, so now we're going to do some more interactive parts. We have copied in this job script, and so now we want to take a look at what is this job script. There are a couple different commands you can use to take a look at the contents of a file. For today, we're going to use more. So just more job script.sh. We're going to be going into the weeds on this one in a slide. For the time being, just notice that everything that starts with that hashtag, that, most of those start with the word sbatch. That's all information for the job scheduler to figure out where to put your job. We're going to talk about that more in a minute. Everything under that hashtag sbatch is what actually happens on the compute node once this job lands there. So the top part's kind of your ticket, and the bottom is your destination. You know, what is going to take place, one command after the other. We call it a job script because it is like a script. It's like once the compute node gets this, it will read these commands one after the other and execute them. So what is the script doing, right? The first thing that it says is module purge all. The second thing it says is module load Python. So this is about how on Quest we use this module system for software. Software on Quest. There are so many different software packages that people want to run on Quest that we do not install them all. In fact, we encourage you to install your own software if possible. That said, there are software packages that are used across a wide swath of the community, so they are installed centrally in this module system. What these two commands are doing is the first one is saying, if I have any modules loaded, I want to just purge them all. We're going to start with a clean slate. That's because sometimes when you launch jobs, that job might remember the modules that you had loaded on the login node when you submitted it. And we just want to clear the slate. The next one is module load Python. So that says, I'm going to load in the version of Python that's the default version on Quest, which is Python 2.7. And then when I run Python code later in this script, that's the version of Python it's going to use. We're going to look more at modules in just a second, but I want to finish walking through this script. The last two lines, bash, and then this project's intro, whereami.sh. So that's a little program that just is going to ask the question, what's the name of the node that this is running on? So when this runs, it'll get placed on a compute node and it will ask the compute node, what's your name? And it's going to put it in to our out file for us so we can see the name of our compute node. The last line is running a Python script that's hello world. So hello world, of course, is the traditional way that you run code for the first time, either in a language or on a device. And in this case, it's just going to write hello world after a bit of a wait so that we can see that job while it's running. It's going to sit there, and then it'll write hello world into a file. So back to the modules. How do you know which modules are available and if the software you want to run has a module? Every command related to modules starts with the word module. And then the next one we're doing is the word avail, which is shorthand for available modules. We hit return. So a lot just flew by there. We can see we've got MPI, BWA, Intel, R, we have lots of Python, lots of different modules are there. So this can be overwhelming. Instead, you can do module avail and then a keyword related to the software you're curious about. So I'm going to use Python for this example. And now it's showing me the different versions that we have available for Python. We're going to go back to a couple more slides here. We talked about the scheduler. So you know we've talked about the compute nodes and we've talked about the login nodes. The scheduler is a computer that sits, you can think of it as a node that's sitting between the login nodes and the compute nodes. And what it does, it's sort of like an air traffic controller. It's keeping track of all the jobs on Quest all the time. Remember when we saw the cores and how that a core can have individual jobs from individual researchers. So a node could have as many as 40 jobs from a researcher at one time. So we can have as many as 25,000 jobs on Quest at any given time. They all have different start times and end times. They need different resources. The scheduler is the program, which is in the node, it's keeping track of all of that all the time on Quest. With the scheduler, when you're on the login node and you submit a job, we're going to do this downstream of this slide, that will go to the scheduler, and the scheduler will look, that code will take a look at all the things you're asking for and who you're specifying is going to be paying for it, right? Your account. What account is this under? What partition, you know, what kind of node do you need? How many do you need? How many cores? It looks at all of what you're asking for. And then it looks at everything that's running out on the compute nodes. And it figures out whether it can place it right away or whether your job has to wait for those resources to become available for you. And so it'll hold your job until then and then place it for you. Once you submit your job, you can walk away. The scheduler is going to take care of everything about placing your job, and then you don't really need to get involved again until your job has completed. And when the scheduler places jobs, then they start to run. Some terminology that's been popping up here that I think should be clarified is account versus an allocation. So your account on Quest is private. That's yours. It's got your home directory /home/your net ID. As I said before, it's backed up. It's got that 80 gigabytes of storage, and it's just for you. If you belong to an allocation and then you belong to another allocation, you'll still have the same home directory. That's your account on Quest. An allocation is a group of people, typically, who are sharing some resources. So they're sharing access to time on the compute nodes. So how much time or what priority jobs are when they land on the compute nodes. And this group also, an allocation, will share storage related to a project or an allocation. So storage related to allocations is always in /projects/the allocation name. This is not backed up. So it bears repeating. If it's catastrophic, if you lose data that's in your projects directory, make sure that it's backed up somewhere off of Quest. So there are a couple of different allocation types. Let's start by talking about general access allocations. These allocations, you apply for them, they are annual, and they are free. So a Research 1 allocation gives you 500 gigabytes of storage, not backed up, and it's designed for your computational needs are less than 100,000 compute hours a year. So it's very reasonable to wonder, well, how do I know how many compute hours I need? 100,000 sounds like a lot. So if you don't know how many compute hours you need, this is an excellent place to start because you can begin with a Research 1. And then if you find out your computational need is greater or your storage need is greater, you can move up to a Research 2 allocation. A Research 2 allocation will give you 2 terabytes of storage, and it's designed for computational need greater than 100,000 compute hours in a year. So the difference between applying for them is a Research 1 allocation requires about 1 paragraph of justification. The Research 2 application is about 3 pages long, and it requires a computational plan. So it helps to have had the experience of a Research 1 to be able to know how to apply for a Research 2 allocation. In addition to Research 1 and Research 2 allocations, we have classroom allocations. These are designed, again, for less than 100,000 compute hours in a year and 500 gigabytes of storage. So Research 1 and Research 2s are good for a 1-year period. After that, they expire, and then you're no longer able to run jobs in them. You'll also have a 3-month grace period after them in which to move your data off of Quest, and after that, your data is deleted. A classroom allocation is good for a quarter. And then after the quarter ends and finals are complete, no more computation can happen in a classroom allocation, and student data in a classroom allocation is then deleted. Note in this slide that red letter P, any general access allocation on Quest starts with the letter P. If your allocation is P 1, 2, 3, 4, 5, then you know it's a general access allocation. Also, I want to mention that project P is sitting in this representation of disk. So on Quest today, we have 3.5 petabytes of disk that is used for research data. The next type of allocation is a buy-in allocation. Buy-in allocations, so where that little red P was, now there's a red B. Project/B something is a buy-in allocation. There are two kinds of buy-ins. It's either both computation plus storage, or it's just storage. But in either case, it's for a 5-year period. Buy-in nodes, so we're thinking about the cluster. Some of them are purchased by different researchers or research groups, and those researchers have first priority on running jobs on all of those nodes. Some of the general access jobs that are 4 hours or less can also run on a buy-in node so that we can make sure to utilize all of the computation resource that we can for research at Northwestern. I want to mention too, there's one other type of allocation. It's a buy-in allocation called the Genomics Compute Cluster. And some of you may qualify to apply for it. The name of the allocation is B1042, so B, it's a buy-in. It's dedicated to genomics research, and it's free to all genomics researchers at Northwestern. There's 2,600 cores, and we have some high memory nodes. We have 175 terabytes of scratch space. If this is something that you're interested in learning more about, please don't hesitate to reach out to me or open up a ticket, and I can reach out to you, and we can get you the application for that. All right, we've been talking about compute nodes and login nodes and the scheduler. There's another type of node, and it's called the analytics node. So we have a couple of analytics nodes. They let you run RStudio or Jupyter Notebooks or SAS Studio just from your web browser. And they each have 512 gigabytes of RAM. So it's it's got some juicy opportunities to use big data sets on those. So I'm just going to show you what that looks like. You can log in if you have a Quest account. You just log in with your username and password. The RStudio one, this is the link that you would use for that. This is in our knowledge base. We'll talk about that in a minute too. The Quest Analytics nodes can only run one version of R or Python. And so the R version that is running there today is 3.6.3. But you can just the way that we logged in through FastX, you just log in to RStudio and then you can use it right away with the GUI involved. Here's an example for Jupyter Notebooks. So you would go to jupyter.questanalytics.northwestern.edu. That's running Python 3.7.1. Again, you log in with your Quest credentials, and then you get your Jupyter Notebook, and it's looking right away in your home directory on Quest. The same with the RStudio, you have your files right there. General access users have access to a number of high memory nodes. We have 512 gigabytes of RAM and 1 terabyte gigabytes of RAM. So sometimes you'll end up where you just really need a lot of RAM. For example, microbiome researchers often need a lot of RAM to do the multi-dimensional matrix, to do alignments for multiple organisms at one time. That's just an example of when you might need it. We also have GPU nodes. So GPU nodes are increasingly becoming more widely used. They are for machine learning or model training, different AI applications. So if you have a general access account, you can use either one of these, and you can find out more about them in our KB. What is the KB she keeps talking about, you may ask? So KB stands for knowledge base. It's at kb.northwestern.edu. We have written in a lot of documentation around Quest and using some of these resources. They're all documented there. So if you go to the KB and type in Quest, you'll get back a list. We have 46 today different bits of documentation around Quest and using Quest. So you can see we're talking about using RStudio Analytics nodes, getting started, quick start guide. I just want to encourage you to check this out. It's a useful resource for users on Quest. I mentioned that if you have data in a projects directory, that is catastrophic. If you lose it, you need to have it backed up somewhere. So these are some of the options that you have at Northwestern for backing up your data. Northwestern Box is unlimited and free. There is, however, a single file limit of 15 gigabytes. So this is a useful resource for some researchers, but for example, over in genomics, this is a pretty significant barrier to make it not the premier place to back things up. But this is a resource that's available to you. Across the university, you also have access to the Research Data Storage Service. So Research Data Storage Service is a paid service for backing up into a backup system that has a copy both in Evanston and in Chicago that are synced on a 15-second cycle. So it's highly redundant. The FSM res files piece of that is also part of that same system. However, Feinberg has paid for it to make it unlimited and free for Feinberg researchers. So if you're associated with Feinberg, that's a fantastic deal. Just encourage you to look into that. Another option that some people use is Amazon AWS using an S3 bucket. We don't provide that. Northwestern does not provide that. However, we do have some tools on Quest that can make that more smooth, as well as other cloud providers. So if you'd like some help setting up some backups to the cloud, just go ahead and email quest-help, and we can help get those tools in your hands. Our preferred, so best practices, preferred method of transferring files is Globus. So to use Globus, you go to globus.org. And then you log in, the upper right hand is a login button. So Globus is connected to the federated logins of a lot of academic institutions around the country and around the world. So when you click login, you'll be asked to select your institution. You select Northwestern, and then you can go ahead and use your Northwestern credentials to get started with Globus. I am not demoing exactly how to set this up. We just don't have time to really get into it today. But I did want to just highlight a couple of things. When you want to transfer files, you're asked to search for a collection. Just use the word Quest for your collection, and you'll see, for example, we have RDSS, so that's that Research Data Storage Service. And then Quest is the third one down. You can see then that you can use Globus to transfer files between Quest and RDSS, or Quest and FSM res files, or Quest and another institution, or you can set your own computer up as what's called an endpoint in Globus, which is what I've got here in this screenshot. So you can transfer files from your desktop up to Quest. Again, this isn't an in-depth demo, but basically you would select the file name, and then you would just say, on the bottom, you see those two buttons that say start. You would just say start either to Quest or from Quest to your local machine. What's really nice about Globus is it's highly parallelized, and it's also very redundant. So it brings the data down and then double checks and makes sure that your data has complete integrity from the original source. We're going to be submitting a job. As I mentioned before, this first part of a job submission script is the communication your job is doing with the scheduler to talk through what resources you're going to be needing. So let's take a look at this in detail. So this is the top half of a job submission script. If it was a complete job submission script underneath this, there would be things like module purge all and module load Python, and then some Python code as an example that we're using today. So the first line is saying what language this job submission script is in. And it's a bash script. Bash is a programming language that's commonly used on Unix systems. It's been around for a while. It's powerful. It's obscure in some cases. So if you want to learn more about it, there are a lot of resources online. By the way, these commands, these lines do not have to be in any particular order. The first one, though, in this particular example is -A for your account. Your account, in this case, is your allocation. So when we did groups earlier and I asked you to note the allocation names, your submission script needs to have an allocation in this field that has compute hours associated with it. So if you're in a general access allocation, it'll be P and then a bunch of different numbers. The next line is P for partition. So a partition is the collection of nodes that in the cluster that your job is eligible to run on. So for example, if you were going to run on a GPU node, you would use you'd use Gen GPU as your partition because you'd want it to run on the collection of nodes that are GPUs. If you can, however, running on the short partition is a good idea because it's the biggest partition available for general access on Quest. Short means that a job can run for 4 hours or less. We'll be using short for the P allocations when we launch a job later here. We need to specify how many nodes we're asking for. And as I said earlier, a good rule of thumb is to use nodes equals 1. So that's -N1. If you know you can run on multiple nodes, then you're welcome to request more than one, but just double check and make sure your software knows how to take advantage of that. If you reserve it and your software doesn't know how to use it, the nodes you reserve beyond the first one will sit idle. Number of cores. So this is we can either specify this as -N1 or -N tasks per node equals 1. So this is saying how many cores. In this case, we're setting up a very lightweight job because we don't want to ask for a lot of resources, because the more resources you ask for, the longer your wait is for your job to be placed. And today for our demo, we really just want to have a job go and land right away. So we're not asking for much. We're just saying we want 1 core on 1 node, and we only want it for 4 hours, for example. So length of the job, this is hours, minutes, seconds. As I said, the short partition is for 4 hours or less. If you asked for 5 hours on the short partition, this job would not be accepted by the scheduler because the scheduler knows that the short partition can only accept jobs up to 4 hours in length. The length of the job is a hard stop. Once your job starts, if it hasn't run to completion at the 4-hour mark, the scheduler is going to kill it. So you might wonder, well, how much time should I ask for my job? Because if I don't know at all, what's best practice? So in that case, ask for the maximum time that partition lets you run for. So on the short partition, that's 4 hours. On the normal partition, that's 48 hours. And then on the long partition, that's a week. Your wait times go up the more time you ask for your job. But if you really don't know how long your job is going to take, what I would recommend is run on the normal partition, ask for 48 hours. If it comes back in like 10 hours, then the next time you run a job in that class, ask for 12 to 14 hours so that you're reducing the amount of time, and so then your wait time goes down, but you've got some fudge factor in there so that if your job for whatever reason is taking a little longer than you expect it to, it'll still be able to run to completion before the scheduler kills the job. So the required memory. If you don't specify memory for your job, you will be assigned 3.6 gigabytes of memory for each of the cores that you reserve. So in this case, then your default would be 3.6 because under N tasks per node, we're only asking for 1. That's the number of cores we're asking for. In this case, though, we happen to know we don't need that much. So we're saying instead, mem per CPU. So remember I said cores can be called CPUs or processors. In this case, you can kind of mentally think of that as mem per core is 1 gigabyte. So we're asking for less than the default. And this is part of our strategy to get this job placed as soon as possible. You can also increase then above what the default value is. You can ask for more memory than 3.6. Well, we'll look at the command that'll give us a profile of how much memory your job uses so that you can fine tune this if you want to. You can name your job. The fields above this one were all required. From this on down, these are optional. So you can give your job a name for your own accounting purposes. And you can ask that all the output go into an out log and all the errors go into an error log. If you don't specify, then they both go into the same file, which is also fine. It's your own preference for how you want to handle the output of your job. All right, so we're getting ready to do the trickiest part of the interactive. What we're going to do is we're going to edit the file, the job submission script. There are two things you need to change. So the first line where it says sbatch -- account, so that's the same as -A, by the way, but it's kind of the long form, so it's a little more clear. Just takes longer to type. When you edit your file, that -- account equals, that needs to be your allocation name. So the convention is that if there are those little angle brackets, that's just to indicate that this is something you need to change. So the angle bracket is not part of what you want to have there in the end. I'm going to do this too, so you can see exactly how to make this change. But account equals allocation ID, that's your allocation name. The other thing you need to change is the line right under it, and that's -- partition equals, so that was -p on the other slide. We have both of them here so that you can see that they're both valid ways of interacting with the scheduler, so don't be surprised if you see them in the two different forms, the shorthand and the long form. -- partition equals, and then the name of your partition. We have a couple of options for you. I mentioned which partition should you use. We have a couple of options. So if your allocation starts with the letter P or E, use short, SHORT. If your partition starts with the letter B, use that allocation's name. So for example, if it's B1000, use partition B1000. If you're coming in as a B1042 user, so that's somebody who's on the genomics compute cluster, use genomics. And if you're a temp user, so that means you're part of W10001, use W10001. All right, the next thing we're going to do is we're going to edit a file. And I need to tell you about our text editor. So just as a reminder, when you're dealing with Unix command line, your mouse does not move where your cursor is. So when we use this text editor, it's called Nano, we'll start off by saying Nano and then the name of our submission script. To move our cursor, we'll use our arrow keys to move up and down and side to side. And then at the end, when it's time to save and quit, we'll be using commands that are at the bottom of the screen. And we'll use that control, our command's gonna be Control X. And remember, control is that little hat, that little up arrow. And I'm gonna walk you through it. So let's go ahead and do that now. I'm in the directory that has my job script. So I'm gonna go ahead and type nano job script.sh. So that's the file that I have been looking at this whole time. So I do nano on that. And this is what nano looks like. So I mentioned the commands are at the bottom. So like where you see get help and exit, those are all of the commands. And that's when I get to the end, I'm going to do that exit command. For right now, I'm now using my down arrow and now my right arrow to move over on the account line. And I'm going to get past the angle bracket, and then I'm going to go ahead and delete all this. And I'm going to use W10001. So if you're a temp user, this is what you should be doing also. And because I am in the temp user allocation, for my example. My partition is also W1000W. And you can see then for the rest of the script, the nodes, so we're reserving one node, one core. The time on this is 10 minutes, so it's a really small request. I'm requesting 1 GB of memory for that CPU. My job's name is sample job. My output is going to go into outlog and my errors are going to go into error log. Once this job lands on the compute node, it's going to purge all modules, load the Python module. It's going to write where I am into my outlog, and it's going to run this program, the Hello World program, that's going to write Hello World after waiting a little bit. So this is now the moment where I want to save. So I'm going to do my control key and the letter X. Little x, not capital. If you've done this part correctly, you will now get save modified buffer. Don't answer no. We want to answer yes. So I'm going to answer with a capital Y. So I just typed capital Y. It didn't show that. But now it's saying file name to write. So at this point, if I wanted to change my file name, I could. I want to keep it the same. So I'm just going to hit return. And now I have edited my file. I'm going to confirm that I've made these changes. So I'm going to do more jobscript.sh. And there it is. So by the way, on the lines that have allocation and partition, you see after that the hash. So that is then a comment if you have the hash in the top SBatch lines. The next step is to send this to the scheduler. To do that, I'm going to use the command sbatch and then the name of my job script. The type of scheduler we run on Quest is called Slurm. And any command that is going to get the attention of the Slurm scheduler starts with the letter S. So that's why this is a batch submission, but it starts with S. So it's sort of secretly saying slurm batch jobscript.sh. So here we go, hit return. I got a job ID number right away. That's always a fantastic sign. So I'm going to type saccount-x. When I did the sbatch part, I got a job ID number. That means that the scheduler has accepted the job and will put it on a compute node. That doesn't mean it's going to run correctly, because I might have had a syntax error or something else wrong in my code, but I know it will be placed on a node and what I asked to happen will take place. The next command that I ran was saccount-X. The saccount command shows me all the jobs I've run in the last 24 hours. The -X part isn't necessary, but it helps clean up the output. So I've made it a habit for me to always use -X so that when there's complex output, it's always unambiguous. You can see that the entries we get for saccount include my job ID, my job name, the partition that I ran on, the account, the allocated CPUs, so that's how many cores it's on, and its state. So right now it is running, and the exit code. The exit code is not valid until the job ends. An exit code of 0 in Unix is always a good sign. So now I want to see what's happening with jobs on Quest in general. How many jobs are there out there? What's running? So we're going to run a command where a lot is going to go flying by. This command is called sq. Again, Q, but with the S in front, so it's slurm Q. When you see my output, it will not match your output. This will only show you the jobs running in the allocations and partitions that you have access to. Because I'm an admin, I have access to a lot of things. So it actually didn't take that long to go flying by. But you can see, I'm going to scroll up here. We have a lot of things running in the long queue, the Gen GPU, I saw short, genomics, more long. These are all running jobs. I know they're running jobs because the fifth column is capital R for running. So you can see there's a lot going on here. And then I'm still going up because I want to get us to these. Okay, so these jobs say PD. Okay, the fourth column here is PD. That means pending. So these are jobs that are waiting to run. Now, on Quest, your job gets placed on a node based on a couple of things: how much you're asking for at any given moment, and also what your priority is. When a resource like Quest is shared between a lot of different people, there are a couple different ways you could do it. You could say first person in gets to, first in, first out. If you're there, then yeah, you've got it ahead of somebody else in line, and so your job gets to run. But that's not always fair. What we have on Quest is called fair share. And the way fair share works is it keeps track of how many jobs each user has been submitting. So say I've submitted a lot of jobs lately, and say Alper hasn't, and we both submit a job at the same time, or even I submit a job right before Alper does, his job's going to land before mine because, to be fair, I've been using the resource a lot and he has not. One of the ways that you experience fair share is if you haven't been using Quest in a while, or if you're new to Quest, your priority is pretty high at first. If you run a lot of jobs, your priority will start to go down because you're taking a larger share of the computational resources than other people on Quest. If they aren't submitting jobs, you can still keep submitting and landing those jobs. But if some of those users who haven't submitted jobs submit at the same time that you do, that's going to step in front of you, which is going to make your wait time a little bit longer. It's an algorithm that's deployed to ensure an equitable distribution of the computational resources on Quest. All right, I am now scrolling back to the bottom, which is going to take me a minute because there were so many of these. You can see also which nodes they're running on. So that last column that says Q node, those are all names of compute nodes.
I have one more comment. So some of you may have storage only allocation starting with B. So in that case, that means you don't have access to compute nodes. And then when you do, like for your allocation be something and then your partition be something, you may get a QoS error. So like an invalid partition or account name. So this may happen if your buy-in allocation is for storage only.
So that's a very important point, because there are definitely groups that do that. They purchase storage, and then for their computes, they either use general access or they use the genomics compute cluster. As a reminder, there is the groups command, which shows you all the allocations you have access to. So any allocation that lets you launch a job is also going to be listed here. So if the one that you picked did not work, you'll probably need to use one of the other ones that's listed when you type groups. All right, so I want to see if my job is done. So I'm going to do saccount -x again. And it is. So this is that same job ID, and now I see that it's completed. So I mentioned we have a utility that lets us identify how much memory jobs use, and we'll do that now. So that's SEFF, so again, S for Slurm, EFF is for efficiency. And now we need to type in the job ID number. I'm typing mine in, yours is going to be different. It's the number that's on the far left-hand side of your screen. The output to this command shows me that just from the top, my job ID number, it ran on Quest, the user in the group, state completed. This is really important to note because SEFF only gives valid information for completed jobs. If your job failed, or if it's got that out of memory error, or if it's died for any reason besides completed, it will not be giving you valid information. the number of cores it ran on was 1. So my CPU I utilized 1 second of CPU. So my efficiency on this is not even 1%. So if I was going to run this job a lot, I would probably need to ask for less memory because that was much more memory than my job needed. When it says job wall clock time, so wall clock is a concept in high performance computing of the amount of time a job actually takes, like if you're looking at your watch. So what other kind of time could it take? When we talk about compute hours, for example, if you're running a job on 10 cores and your job takes 1 hour, that was actually 10 compute hours that took. But the wall clock time for that job was 1 hour. So just some additional terminology that we use in HPC. So the job wall clock time, how long did it take? It was 1 minute and 41 seconds. The memory it used was 6.6 megabytes, which means it didn't even hit 1% of that 1 gigabyte of RAM that we reserved. So again, if I were going to run this frequently, I would decrease those numbers to more accurately reserve what this job was going to use, and then decrease my wait time thereby. So it decreases the wait time because there are more places I can run. The smaller my request, the more places the scheduler can tuck me in between other jobs, or like if a node is running on 6 cores, but there's like a little gap where a small job could fit in before the next job lands, the scheduler can place me in it. All right, so I did the SEFF. So now I want to look at my job output. I'm going to do ls. So ls again is list, but I'm also going to look at ls-l. So that's the long form of the list. I just wanted to make sure we took a quick look at that. Permissions for files are the beginning of these lines. So where it says -rw, that means I have read and write access to that file. The second RW means anybody in my group has read, write access to that file. So that would be my allocation. And then that last R means that anybody on Quest can read this file. And that's not necessarily what I would do for my own research files, but for an example file that makes sense. The owner and the group are the next 2 fields, and then the number is the size of the file. So I can see right away that I had no errors because my error log is size 0. So nothing was written into that file. The outlog, however, has something in it. So let's take a look at that. We're going to say more outlog. And we can see, do you remember the program ran and it was identifying the name of the node on the compute node that this job ran on, and that was QNode 5056. It also was telling me what directory that the job was submitted from, and there's that hello world. And in fact, I also wrote, or the Python script also wrote that into the Python output.txt. So I can do that, more Python _output.txt. And there's that hello world text right there. What I want to do next is submit an interactive job. So what we just did is we launched what's called a batch job. So that's where I've written all the commands in advance. I can send the job to the compute node. It runs to completion. I can be off getting a coffee or doing whatever. And then at the end, it writes my output and I'm done. Another type of way we want to use compute nodes, though, is we want to launch interactive jobs, which lets us interact with it the same way we've been doing here with the login node, except on the login node, I have these constraints, right? I can't use more than 4 gigabytes of RAM or 4 cores, but I could launch an interactive job that would let me have a whole node. I could have 150 gigabytes of RAM and 30 cores. So if I wanted to do an interactive job that required more computation, I would need to ask the scheduler to reserve that for me and tell me where I could log into. So for example, this QNode 5056, because it's a compute node, I can't just log into it. I have to have a job running on a node to be able to get on it. So let's do that. This command is a little bit more, this is probably the most involved of what we're going to type out here. It's, again, it's in the script, but we use salloc. So S for slurm, the alloc is to allocate, dash capital A, so this is the allocation name, and I'm going to use this one, W10001, and then dash P for the partition name, which in my case is the same. So of course, if you're doing this for yourself, your dash A needs to be your allocation and your dash P needs to be your partition name. All right, now we need to do the time, dash T, and I'm going to do 0 hours and 10 minutes and 0 seconds. And now I need to do the number of nodes. And remember, this is always 1 unless you know it needs to be higher than that, but your default should be 1 on that. And then this is the number of cores or processors I'm going to reserve, and that is also going to be the number 1. It's got the same basic information that we had in our bash submission script. So I'm going to go ahead and hit enter on this. This request is going to the scheduler and it's come back with a job ID number for me because this is a job. And now it configured the resource for me and assigned me a node. And it's actually the same node I had before, QNode 5056. That's because that's one of the nodes in W10001. So this node is now ready for me to log into it. So the way I do that is SSH and then QNode 5056. So that was that bottom line where it says nodes QNode 5056 are ready for job. So I can go SSH, I have 10 minutes where I can log in. And so now, if you look at my prompt, it's my NetID at QNode 5056. So just to confirm that I'm not on the login node anymore, I can run the W command here. And now, instead of seeing many, many users, there are just 3 of us here. I can also run the top command, TOP. And this is going to show me all the processes running on this node right now. So if you really wanted to get into this, you might need to learn more about the different options here. We use this for debugging. Like, for example, say you thought that you were running a job with 10 cores. You can use the top command on a node to see how many processes are actually happening. And if you only see 1, then you know you're not actually running on 10 cores. So this is the top command. I'm going to get out of it by typing the letter Q. So that's just the letter Q to get out of top. Now, to get off of this node, I can either just hang out here for the next 8 minutes and then I'll be booted off because the scheduler, when you reach the end of your time zone, just kills your job. Or to gracefully exit, I can type log out. And what I logged out of was that compute node, which means I'm back at the login node where I started from. So for more information about commands like top, what you can do is you can do man and then top. This is man pages. This is the documentation that's available on Unix systems. We can look through this. I find that a combination, when I want to learn more about a command, I will Google it and I will use man pages. They're kind of both helpful. I'm going to type the letter Q to get out of that man. But that's one way you can learn more about how to use these commands. I want to do one more thing, and that's going to be we're going to launch a job and cancel it. So I'm going to launch the same job I did before. One of the things that I like to do things without having to type so much is instead of typing sbatch and then the name again, I can do this, which is exclamation point, which is has a fun nickname in Unix, which is called bang. So I can go bang and then sbatch. And what that's going to do is it's going to do the last sbatch command I did. So I'm just showing you this because this is kind of fun to type less, which we're always big about typing less. So I'm going to do this sbatch. So it's submitted again. And now I'm going to do cancel. So say I submitted and I realized, oh no, I don't want to do this. So I can cancel my job. And now if I do saccount -X, we can see that I had a job that I canceled. The reasons you might want to cancel a job if you know there's errors is it will mean that your priority doesn't get reduced if your job doesn't run. So say I'm running a really big job and I know that I want it to run a different way. If I cancel it and submit it again, my priority hasn't gone down. If I let it submit instead, then my priority is lower for the second time that I submit it.
I have one more note. So some of you may still be waiting on the queue. Basically, if you're using on your own general access allocation with short partition, there may be some queue already. So it's normal if you're still waiting, if your job hasn't started yet.
That's a really good point. Quest utilization is it varies a lot. So some days are light days and some days are really heavy days. And some things we can predict, like we can say definitively that May is busy and November is busy. And the end of quarters tends to be busy. But projects land at irregular times. So how long you need to wait for a job can vary. And the takeaway from that is that when you are designing your project and you're planning out your computation plan, build in some time so that if sometimes your jobs take a while to land, that doesn't negatively impact your ability to complete your research. In the event that your job doesn't actually get placed before the end of the workshop, that's fine, because you can just complete the commands as they're laid out on the GitHub if you'd like to do that. We have reached the end of Introduction to Quest. I want to reiterate, though, that we have a ticketing system, quest-help@northwestern.edu. It reaches all of the consultants, and we're really passionate about facilitating research, computational research at Northwestern. So we're happy to help, and don't hesitate to reach out. If you have any questions at this point, please don't hesitate to drop them in the chat. We have 10 minutes. We can talk through whatever it is that you're interested in learning more about. So I have a question that I got about what's the easiest, most efficient, and correct way to back up from Quest to my local hard drive. So our recommended best practice there is to use Globus. So Globus is both talked about in the slides and also in our knowledge base. Gives you a point for point, but the advantage is using Globus is it's fast and it's highly redundant on making sure that your data is completely transferred. It's also easy, once you get a hang of the interface, it's straightforward to select files you want to copy from Quest to your local hard drive. It is a fire and forget. Once you do it, you can walk away. You just have to make sure your computer doesn't turn off. So it can still complete the transfer. All right, I have a question about using a Conda environment. I have some extra slides. So this is talking about Python package installations. So there are a couple of different ways regarding Conda. I would just really encourage you also to look at the KB for that. The knowledge base, we have we go into that with detail because a lot of people need to use that. But you can install things locally, and you can set up a Conda environment so that you can have the packages that you want even as you do module load so you can do module load Python and then have your own packages that otherwise require system installs available just to you. Alper, do you have more thoughts on using a Conda environment?
So yeah, I mean, Conda environment, I think, are the best practices, especially when you're containing your software so that you don't interact with anything else. So you can create your own environment with the software you need, and you can keep that so you can use it anytime, right? For reproducibility concerns, eliminated with using Conda environment. So you can keep that Conda environment, and later if there's a new version of your software, you can use another Conda environment and install it there. So you will not use the previous one or the previous results. So I think it's a good practice to use Conda environments on Quest. And you can use your own environments. You don't need to help from the admins. So you have permission to create your own environments. So it will be faster for you to just create an environment, install your software, run your software.
So I got a question about, do we have Python 3 on Quest? So yes, we definitely do. I'm going to do this module avail Python again. So when you see something with a D behind it, that means it's default. So when the code did module load Python, it actually loaded as the default was Anaconda. So I can just write source activate my env in the job submission script. Yes, exactly. So anything you can do on the command line, you can do it in your job submission script, one line after the other. Our package installation, again, we have a lot of documentation around that because a lot of people are doing this as well.
I mean, in general, our recommendation is to first try local installation. The reason of which, because if we try to do this on the system level, that may create issues, like all sorts of issues because of the dependencies and contradictions between the packages. So we try to avoid this to help everyone, actually, help everyone in the cluster, because you don't want one of your package work one day and then the other day it doesn't work. So the best practice is to try to install locally. You can do this with environments in Python, or you can do this with R. So you can just, basically, this is installing in your home folder. And then you don't need to worry about what's installed on the main distribution or the module. So you can always use your own local installs.
It's especially important for reproducibility. You want to make sure that every time you run a job script, it's running exactly the same libraries. And if you have them installed locally, you can guarantee that.
As I mentioned, generally the initial recommendation is to try to install or compile your own packages, but this is a bit more complicated or may require more experience. If you have experience with compiling your own packages, you're welcome to do it on Quest. So basically, you can compile, create the binaries or the executables for yourself, and run it from your home or project folder. But if you don't have that expertise, definitely reach out to us. Send it email to quest-northwestern.edu. So we will go back and help you, come back and help you.
Just a couple other things to know about Quest. We have an annual downtime. We haven't scheduled it for this year yet, but it's typically around a week when Quest will not be available. We'll let you know about it at least 2 months in advance. When there are system things to be aware of on Quest, that message of the day at the bottom, it'll show any announcements of changes coming up or of the downtime, or if we're experiencing any systems difficulties at that moment. I'm speaking for myself, but I know for Alper too, we're really happy to be able to facilitate research at Northwestern. You guys are doing a lot of really interesting things, and it's cool to see computational research increase, and both in breadth and in depth across all of the university. So thank you for coming today. And if you have any additional questions, don't hesitate to reach out to quest-help@northwestern.edu.